So in today's session, we are going to enter into chapter 2. And it's titled Acute Angles and Right Triangles. And so what we're going to do in this first section of chapter 2, so a few things here. We're going to look at the basic trigonometric functions, which we looked at and introduced in chapter 1, which is sine, cosine, and the other 4. And we're going to look at those applied to acute angles. So remember, acute angles are the ones that are like less than 90 degrees. So we're going to redefine the functions again. So in chapter 1, we were kind of looking at circles, and we defined the trig functions based on an angle and a point on a circle as being like the y value on a unit circle, or the y value divided by the radius, or something like that. We're going to define our trig functions again just by focusing on the triangles that you might have in that unit circle. So we're going to have what's referred to here as a right triangle based definition for the trigonometric functions. And anyway, so then we're going to look at how function values change as the angles change, what kind of answers you get. And all of these things could be seen when thinking about the circle or the unit circle in that definition that we did in chapter 1. But all trig books provide both types of definitions for the trig functions. And these are referred to as the triangle-based definitions as opposed to the circle-based definitions. So here's a summary. Right triangle-based definitions. Let A represent any acute angle in a standard position. So they're talking about this angle down here. And so then if you take the sine of that angle, then in the triangle you get that from, there's a y, which is the height, there's an x, which is the base, and there's an r, which is the length of the diagonal side. And again, they're using the same letters they used when the point B on the diagram here was in a circle. So you can translate all of this to our circle definition if you just imagine that there was a circle here. But they're just saying when we just look at the triangle here, then when you have an angle and a triangle, so here's angle A, then sine of A will be the side length y divided by the side length r. So this r, what would be the radius of the circle, this gets a new name for the triangle, which we may recall. This is called the hypotenuse. So when you see the r value given in all of these definitions, you also see the word hypotenuse. So the sine of the angle is equal to the side opposite the angle. So when they say that's the y value, they're showing if here's angle A, if I go opposite of A, you'll see that side y there. And so that's going to be opposite, and then that's going to be divided by the hypotenuse. So the side of the angle is equal to the opposite side in the triangle divided by the hypotenuse of the triangle. And of course, this is when we have an acute right triangle, an acute right triangle. So we have a right angle and acute angle. So similarly, the cosine of the angle, which is here, is x over r from our circle definitions. But in this triangle, the x is now the adjacent side to the angle. So the angle A is here, and then the x side right there on the bottom is the one right next to the angle there. That's not the hypotenuse. So they call that the adjacent side. And so the adjacent side divided by the hypotenuse, and we write that as the cosine is equal to the adjacent divided by the hypotenuse. And then the tangent Well, we know that's sine over cosine, but if I make sine over cosine and they both have the h's, those cancel, you end up saying that that's the opposite side divided by the adjacent side. So opposite divided by adjacent is here. So that means that the tangent is equal to the opposite side divided by the adjacent side. So this is a way when you're looking at a triangle to think about what's going on with these trig functions without having to go back and imagine the circle that I drew that's around the triangle and all that stuff. And instead of trying to think of a corner and a point, you can just look at the triangle and make the ratios of the sides to define the trig function. It ends up being exactly the same as when this triangle is sitting inside a circle. It goes exactly back to the definitions in chapter 1. But the reason we give these separately is that when you're just looking at triangle, you don't want to have to think about the circles. It gives you a very direct way to come up with the values and the definitions for these. So we'll get more comfortable with this if we see it in action, I think. But right at this moment, does anybody want to ask a question about what's on the screen that I could explain better or elaborate on? So of course, we could look at the other 3 of the 6 trigonometric functions here. Yeah, there's a SOHCAHTOA here that's helped me a lot. I'm going to definitely summarize that on the screen in a second. Thank you, Tejas. The other 3 here, cosecant, secant, and cotangent, remember, they're all just flips of the sine, cosine, and tangent. And so if you just think of each one of these fractions being turned upside down, you get those other 3 automatically. But let's look at that recommendation that was just been suggested in the comments. The reason I've written these this way, look at this box here, is that there's a little sort of pneumatic, meaning a word with the letters that you can make out of this to help remember these. So if we spell this out, SOHCAHTOA, SOH. So that part is that the sine is opposite over hypotenuse. CAH, that's that the cosine is the adjacent over the hypotenuse. And then TOA, that's that the tangent is the opposite over the adjacent. Then this can be like a word, and this is like SOHCAHTOA, SOHCAHTOA. And so SOHCAHTOA is a way of trying to remember these basic triangle definitions by putting the letters representing these relationships into a word and trying to make a sound out of it. SOHCAHTOA. And maybe that'll just help you remember. If you just remember that it translates into these 9 letters, then you'll remember these definitions. SOHCAHTOA. So let's put this into action, because as I mentioned before, the best way to get comfortable with this is to put it in action. So here's a triangle, and they're telling us the 3 sides of the triangle. This is a right triangle. You could even see that 7, 24, and 25 will work in the Pythagorean triangle. 7 squared plus 24 squared equals 25 squared, as an example. Find the sine, cosine, and tangent values for angles A and B. So let's say we began by saying, I want to find the first one they asked for here, which is sine of A. So first we want to identify where is angle A. And we can see that's the angle with the vertices A described there. So that's angle A. And so now for the sine, we may want to remember that SO of the SOHCAHTOA means that sine is opposite over hypotenuse. So that means sine of A will be the opposite to the A angle, which is 7, divided by the hypotenuse, which is 25. And that's it. So the sine of A, the sine of angle A in this right triangle will end up being 7/25. So if you have a right triangle and you know the three sides, then you can get the sine, cosine, tangent, or all of their reciprocals of any of the angles in the triangle, just on the basic definitions of the values of these functions. Questions about this first part of the example? All right, so if I was then saying I wanted to find the cosine of that same angle, so the cosine is the adjacent over the hypotenuse. Adjacent to angle A is the 24. Hypotenuse is still 25, so that would be 24 over 25. So that tells me that the cosine of angle A is 24 over 25. Questions, comments, discussions about that?
I don't know if this makes sense, but I found it seems there's a pattern. So sine is y over r, cos is x over r, tan is y over x. The pattern is y, x, y, and they are all divided by rx, rrx. Now, when you turn this down, you get you get the values for CSC and CEC, SEC, sec, and cot. So basically, the top, when you reflect the top, let's say sine, cos, tan, you get the bottom three. I don't know if it makes sense.
Yeah, that's kind of a strategy. Like, let's say we wanted to do cosecant of angle B, just to sort of help us go through this idea in general. So we could go back up here and say, well, cosecant is the hypotenuse divided by the opposite. Hypotenuse divided by opposite. We could also remember that cosecant is the flip of the sine. And since sine was opposite over hypotenuse, then cosecant will be hypotenuse over opposite, which is what that definition is showing also. But instead of having to look it up, hypotenuse over opposite, we could remember that it's the sine function upside down. So I would say, where's the B angle? So the B angle is up here. And then to get cosecant, I would do hypotenuse over opposite. So that would be hypotenuse over opposite, which would be 25. And the opposite to the B is 24. And then that's the answer. Oops. Cosecant B. So in this way, you can either refer back to these side fraction definitions, or you can just remember sine and cosine and everything else comes from that, or remember SOHCAHTOA, and then the other three are just the flips of one of those three in order to get any of the six that you might want. So they just asked for sine, cosine, and tangent here. Maybe the next one they ask for the other ones. I think we're just supposed to do more of the same there. Yeah. Anyway, so that's the idea of how you can get any of the 6 trigonometric functions when you have a right triangle with acute angles in it, meaning all the angles are less than 90 degrees. You don't have an obtuse triangle or any of those other types we looked at. Then you can get the trigonometric value of those 2 other angles in there quite quickly by using these ratios of the correct sides from the triangle. Questions, comments, discussions about that at all? Okay, I don't know what they have here. This slide is not really complete. For any acute angle A, co-function values of complementary angles are equal. Yeah, so basically what they're trying to show in a slide that wasn't completed very well here, so I apologize for that, is that one of the things we can observe, let's use this empty slide to observe that if I have angle A and I'm realizing that the 7 side is opposite to the A angle. Well, we can also notice that with angle B, the 7 side is adjacent to angle B. So if I'm doing sine of A, and I'm recognizing that that's opposite over hypotenuse, that's 7/25. Well, what if I switch now and I'm doing cosine of angle B? So I'm switching from sine to cosine, and I'm switching from the A angle to the B angle. Well, cosine is adjacent over hypotenuse, but adjacent to B is also 7. So what we're noticing is that opposite of A is adjacent to B. And so since cosine wants adjacent over hypotenuse, I get the same thing. And so what these are telling us is that for this triangle, sine of A is equal to cosine of B. Similarly, cosine of A will be equal to sine of B. So this relationship holds, and it holds because the A and the B are inside the same triangle. Now, what do we know about A and B inside the same right triangle in an acute triangle? You may recall this from our earlier work. We called those, well, they add up to 90 degrees. That these are complementary angles, they add up to 90 degrees. So I would say that we note that A plus B equals 90 degrees. And basically, these are going to hold whenever you have two angles that add up to 90 degrees, that the cosine of one of them is going to be the same as the sine of the other one. And it doesn't matter which is which. So to extrapolate this as an example, cosine of 70 degrees is going to be the same as the sine of 20 degrees, because 20 and 70 add up to 90. Or vice versa. Sine of 70 would be the same as cosine of 20. And this will be true anytime the two angles add up to 90 degrees. So that's what they're trying to get at as these co-function identities. These co-function identities are kind of mixed up and rewritten in different ways with different functions in here. But you can kind of see this relationship just by going off the triangle. And that's something that we'll want to get used to and get used to being able to use, that you can set up these kind of equivalencies. By understanding what the definitions of sine and cosine are when we're in one of these triangles, we get these little equations or theorems or properties of these functions, especially when the two angles add up to 90 degrees, because those are these two different angles that you have in an acute right triangle. Questions about that at all? Comments, discussion? So let's see how they might try to put some of this to use. So the way they're showing it in this example here, let's look at this first one, which is kind of from their table, is that the equals overlaps here a little confusing, but it's that cosine of 52 degrees would be equal to the sine of the other angle that adds up to 90. And how do we figure out what that is? You subtract 52 from 90 to see that the other angle would be 38. So that's 90 minus 52, which is 38. So we can just see that 38 degrees and 52 degrees add up to 90. And that when you have two angles that add up to 90, the sine of one is equal to the cosine of the other. So cosine of 52 is equal to sine of 38. And sine of 52 would be equal to cosine of 38. They're going to show that this is the same thing for the tan and the cotan, and the secant and the cosecant. And again, we could see that if we just went back to the primary definitions. If I'm in angle A, then tangent, let's change colors here. And I was trying to figure out the tan of angle A. Well, that would be opposite divided by adjacent. But if I went over to cotangent of angle B, well, now that's adjacent over opposite, but the opposite of B is the adjacent of A, and vice versa. So if I change the angle and I flip the sides that I'm using, I get the exact same thing. So we're also going to have then that tan of A is equal to cotan of B, and vice versa when they add up to 90 degrees. And the same for secant and cosecant. That's what this table was trying to show here, even though they didn't fill it in correctly on the slide. And so we can use these facts here. They're just demonstrating these. And they call this cofunction identities. Cofunction because it's kind of like the function that is the flip of the other one or the pair with the other one. And when you change the angle, then you get that same relationship. All right, so let's look at an example, another example of this, and then maybe we'll take a short break and move on to the next section. Find one solution of the equation. I want to do that. We'll see if time permits. Find one solution for the equation. Assume all angles involved are acute angles. So they tell us that cosine of this angle, which is an acute angle, is equal to sine of this angle over here. And for the cosine to equal the sine, that means that that stuff in there adds up to 90 degrees. So that would mean that from that table, that theta plus 4 has to end up being equal to 90 minus the other one. Or actually, I'll just do it the way I said it. That's the way they did it. I like the way I said it better. Which is that that first angle plus the second angle adds up to 90 degrees. And the second angle was 3 theta plus 2. So that gives me a little equation that I can solve by knowing that this angle and this angle, that they have to total 90 degrees. Then I can write an equation saying they add up to 90 and I can solve. And I would get 4 theta, well, they're going to solve it here. So this is an example of how you can use these co-function properties of sine and cosine, that they come out equal to each other when the angles you're using add up to 90. You can use that to sometimes solve equations or find out missing angles. So of course, once they found out theta, they would have to back substitute theta in there and in here to see what those two angles were. But you could certainly solve for theta if that was the goal of the problem. Questions about this example here? Okay. So then they have another one with tangent, and you can just see with tangent and cotangent, what did they do? They took this one, they took this one, and they just wrote that they total 90, and then they solved for theta. So hopefully problems like this, if they pop up on the practice problems and on the homework, once you see that these are co-functions, tan, cotan, sine, cosine, secant, cosecant, the function and its the word co in front is because of this relationship. Sine, cosine means the co-function to the sine function. Tan, Cotan means the cofunction to the tan function. Secant, cosecant means the cofunction to the secant function.
Professor,
Yes.
can you only like add them in the equations if they are cofunctions?
Well, that's one of the ways you can guarantee that they were 90 degrees. Now, it might be some other problem. You could get an adding because of a different reason, but definitely if you have tangent and sine, you can't do this.
Okay, that makes sense. Thanks.
Only with the pairs of the cofunctions does this process make sense. Great question. All right, so then finally in this section, we want to have a little thought and discussion about increasing or decreasing functions. So if we imagine a triangle being changed by changing its angle and keeping sort of the R side and the X side as they were, then as we change the angle, they're showing it kind of increasing from left to right in these diagrams here. So here we have kind of a small angle, maybe a medium angle, and then a larger angle, just to sort of see the growing of angle A there. Well, what's going to happen in these cases is the Y is getting taller and taller, and the X value on the bottom, if the R value is staying the same, the X value is shrinking. So if the R value stays constant, since it's saying here R is fixed, they're going to fix R, then the Y value is going to be increasing, while the X value is going to be decreasing. That as that angle opens up, since the R isn't getting any longer, then the Y side has to get taller, making it bigger. But since R is pulling everything over to the left because it's not getting any different in size, then that forces the X value to get smaller. And this tells us something about how the functions will be behaving, sine, cosine, etc., by seeing what goes on to the values that make up the function. So for example, sine is the Y value over the R value. And if the R value is not changing, as the angle gets bigger, the Y value gets bigger, therefore the sine is going to be increasing. Similarly, as R stays the same, as the angle gets bigger, the X value is forced to get smaller. The cosine function is X over that fixed R value. So if the X is getting smaller, the cosine must also be getting smaller and must be decreasing. This is designed for us to try to develop some intuition about the behavior of these functions. And we're going to spend time really, like I said, these functions are the ones we're using for the entire semester. So we're just going to go deeper and deeper into trying to get comfortable with what they do and how they work and how we can use them. And so part of that is to imagine what's going on with the functions as the angles that you're plugging into them are changing. Well, tangent is a ratio of sine over cosine. So if I make a fraction where the top, the sine, is getting bigger and the bottom is getting smaller in size, well, then that ratio is going to be increasing. So the tan will be increasing. So that's sort of the introduction and these nice sort of pictures to try to help you imagine why that's the case. Well, this gives us an ability to compare, at least with acute angles between 0 and 90, when all of this is holding true in a triangle. We can compare things like, would I suspect that sine of 21 is bigger or sine of 18 is bigger? Well, since as the angle grows, the sine function is increasing, then if the angle has increased from 18 to 21, then sine of the angle should also have increased. So that's why we can see that this is a true statement here, or that this statement can be made. So in this case, they're asking us to determine whether these are true or false based on our understanding from these relationships. Now, you could check any of these by just typing them on a calculator and comparing the values. So we do want to recognize what they're asking us to do here is to really warm up to the idea of the functions in and of themselves and our own understanding without having to grab a calculator or something like that. But I do always remind people to use technology to support your understanding and your growth. So you could always check. You could say, I believe this is the case, but you could also check it on a calculator. The secant, you could sort of look up from what they said here that that should be an increasing function. You could remember that because that's the flip of cosine. If you flip something that's decreasing, you get something that's increasing. So over here, they've increased the angle, but they're saying the secant is giving you less than or equal to what you had before. But since secant is increasing when the angle increases, and here they're saying it's less with a bigger angle, then we could conclude that this statement is false. Questions, comments, discussions about that? So I'm encouraging students to try to think about what they're saying here, but I'm also encouraging you to get even more comfortable with grabbing your calculator and throwing these functions into your calculator at the drop of a hat, so you can quickly assess statements like this without having to feel like you have to imagine some properties of relationships or things like that. Because that's a little hard to do out of the gate when you don't have any comfort with that, but that will still develop over time if you're thinking about ideas like this. And they obviously have other examples here, not written very well. So we have about 22 minutes left. I would like to spend the rest of that on these three triangles. So we'll just talk about this one section today and see when we can get to the other sections later. I'll probably shoot a video later of a section if we don't get to it. But yeah, these triangles are really, really important. So we should spend the rest of the time today talking about these triangles. So we have first triangle, there's going to be two key triangles that we're going to look at regularly whenever we're thinking about triangles and trig functions with triangles. And this is the first one. So this first one is a 30-60 degree triangle. And if two of the angles are 30 degrees and 60 degrees, then that leaves 90 degrees for the other one, meaning you have a right triangle. So they're showing at this being arrived at in a very common way, that you have an equilateral triangle, which you may recall means that all three sides are exactly the same. And that when you have that, since it's completely symmetric, all the sides are the same, then all three angles will also be the same, being 60 degrees each. So that's a very nice symmetric shaped triangle. But it's not a right triangle. None of the angles in it are 90 degrees. So they're showing, well, what if you just chop this right down the middle? If you just draw a line right down the middle, then you get two triangles that are both 90-degree triangles. And the other degree measurements are the one that was split. The 60 got split into 30-30, and then the others that already were at 60. So this creates this 30-60, 90-degree triangle. And if you make the triangle this way, if you started with an equilateral triangle of sides length 2, well, then when the bottom side got cut in half, then you know what's on each side is a 1. So they're showing over here you'd have a 1, and this side would still be 2. And there would be this unknown side over here that was the height when you chop this triangle down the middle. So when you do that, we can figure out that height because you have a right triangle with only one missing side. So we would know that x squared plus 1 squared is equal to the longer hypotenuse side 2 squared. So x squared equals 4 minus 1, which is 3. So x is equal to the square root of 3. I'm only taking the positive because it's the length of a side. So now we know that these sides are the square root of 3. So if you have a 30, 60, 90 degree triangle where the hypotenuse is 2, then the bottom or base or the side opposite the 30-degree angle will be half of the hypotenuse, will be 1. And then the side opposite the 60-degree side would be square root of 3. So this is a triangle we want to get used to because it shows up quite a lot. Now here's the part where they showed how to figure out what I just showed you, that x is equal to square root of 3. So that means we can then figure out sine, cosine, and tangent of 60 degrees and 30 degrees by doing our ratios in the SOHCAHTOA, or definitions of the trig functions. So for example, if they're talking about the 60-degree angle and you want to get the sine, then you would do opposite over hypotenuse. And the opposite to the 60 is the square root of 3. The hypotenuse is 2. So you get root 3 over 2. And again, you could type that square root of 3 divided by 2 on a calculator and get a decimal approximation to whatever level of accuracy you want, but that's the exact correct value there. Similarly, if I took cosine of that same angle, then I'd be doing adjacent over hypotenuse. Well, that would just be adjacent to the 60 is a 1. So that would just be 1 over 2 or 1/2. So that's a nice number. So this is a case where there's a trig function of an angle that comes out to a nice number. Previously, we were kind of just using 90, 180, 360 when we were trying to figure out the basic trig functions with the circle definition, because those were like 1s and 0s. And maybe in the middle, we looked at the fact that when they're 2 or the same size, you get square root of 2 over 2. Well, that's going to be the second triangle we look at in these definitions here. So this allows us to accumulate some nice values. And if I make a fraction of sine over cosine and the 1/2 denominators cancel, I get square root of 3 over 1, which is just square root of 3. We could do the same thing for the 30-degree, or we could point out the fact that the 30-degree is the co-angle, the complementary angle that adds up to 90. So sine of 60 is going to be the same as the cosine of 30 because of the co-angle thing we were just talking about. Cosine of 60 will be the same as the sine of 30 degrees. So cosine of 60 is 1/2, sine of 30 is also 1/2. So then they say, all right, let's use this to get all the rest of the trigonometric functions. But again, we could just take the 3 answers we got up here and flip them to get the other 3 unspoken for trig functions. Cotan is the flip of tan. Cosine and cosecant are the flips of sine and cosine corresponding. So the next triangle, as I was just discussing, is one in which both of the angles are exactly the same, 45 degrees. And therefore the angles, the sides opposite those due to that symmetry will also be the same. And so if we set those sides to be of length 1, then we could figure out, as they show here, that r is the square root of 2. And then we can do the 6 trigonometric functions for 45 degrees. So they do that here. And we can see, for example, that since this is the same angle, and those are co-angles, then sine of 45 should be the same as cosine of 45. We saw that back when we did the circle because the x and the y values to that point were the same length. But in this case, we get square root of 2 over 2, which we got before, for both sine and cosine of 45 degrees. And if I make a 1 by making a fraction out of those for tangent, we see the 1 show up. And we can flip all 3 of these for the reciprocal functions. So we now put all this information together and we make a function values table of these key angles. The angles we're going to want to imagine that we could come up with pretty quickly. And quite honestly, usually by the end of the class, all students who are still there have memorized all these. That doesn't mean you have to sit and stare at this table until you memorize it, but it ends up being so commonly used, these angles, that you have to recreate them enough times, then you start to just remember the answers. And so it might be helpful to review to this table and look it up in the future. And so that in each of these cases, we can remember these values. I think this question mark here is just supposed to be a degree symbol. Or maybe something, I don't know, X. It's funny that they didn't finish these tables completely. Anyway, but sine of 30 degrees is 1/2. Cosine of 30 degrees is √3/2. We can use these tables for these values. For 45 degrees, we could fill those in because we just had these all given to us here, or we could figure them out. Sine of 45 degrees is √2/2, as is the cosine. And when you make a fraction, you get the 1, and then you flip all of those to get the other 3. But these end up just being values that you want to sort of think you could look up. So now you're going to have lots of times where there are problems where we're going to use sine or cosine or one of the other trig functions for either 30 degrees, 45 degrees, 60 degrees. And of course, we could do 0 degrees by using our definitions on the circle. And we can use 90 degrees by using our definitions on the circle. So these 5 angles are going to be very, very common ones that we want to be able to think of the sine or cosine or any of the other trig function values for 0, 30, 45, 60, or 90 degrees. And then they just have a blank slide at the end. So I still think, so here's the thing I think will help you remember this. Just imagine you have these 2 triangles. One is the isosceles triangle, so maybe that's the easiest one to think of first. If these is an isosceles triangle where these 2 sides are the same, then you know that these are both 45. And if you're on the unit circle, and this is a 1, then you could use the Pythagorean theorem to remind you, or you'll start to remember that these sides are both square root of 2/2. Then the other triangle is where one of the angles is 30 and the other one is 60. So I'm going to mark 30 here because that's the smaller angle, and 60 up here. And if I still have a radius 1, because I'm still going to keep focused on the radius on the unit circle. If I have a hypotenuse of 1, well, then the shortest side will be half of that. Up here, and they're pretty example here, they set the hypotenuse as a 2, so that when they took half of that, they would get a nice whole value number of 1. But, of course, all sine, cosine, and trig functions are always going to be between 0 and 1. So instead, you can imagine that you get that 1/2 value, as I was showing here. Because if the hypotenuse is 1, then the shortest side will be half of that. And you could use the Pythagorean theorem to figure out the final missing side here. But pretty soon, you'll hopefully remember that that's square root of 3/2. It's the only one of any of these sides that has a square root of 3 in it. If you can remember these 2 unit length hypotenuse right triangles, then you can get the 30, 45 degree, 60 degree angle measurements for all of the trig functions by just using these. So for example, sine is opposite over hypotenuse. That's 1/2 over 1. So sine of 30 degrees is 1/2 over 1, or 1/2. cosine of that same angle would be adjacent over hypotenuse, and the adjacent is square root of 3 over 2, etc. So using these properties, you are basically able to recreate all 6 primary trigonometric functions for these common angles of 30 degrees, 45 degrees, 60 degrees. That's what we're trying to get students able to do and to grow comfortable with. And if you think of these 2 primary triangles, that'll basically be what you want to remember. Questions, comments, discussions about this?
Not really about this specifically, but can we find this slideshow like on Canvas as well?
Yeah. So I can show how to do that. Let me stop this session. Any other questions about the slides while we have them here? And then after we leave, I'll show how to find them on my math lab. There were 21 slides. There's another blank one on the end. Yeah, just 20. So really there was 19 because this was slide number 19 where they finished with this table of values. All right, so we will finish up there. I will stop the recording. And let me show you how to find the slideshows so that you can go back over them by sharing the screen here. And then maybe we've got a few minutes left. We might even see if we can take a look at a homework problem or something. All right, so if we go to the main website, then you go to Video and Resource Library. Can you see that on the left here? And then you click on PowerPoints. PowerPoints are these slideshows, and then you can pick whichever chapter or section you want. So we were just looking at chapter 2, section 1. And then here is the slideshow. When you click on that, it'll download the file, and then you need to open that with something that can open up slideshows. So the Microsoft version of that is PowerPoint. That's why these are called PowerPoints. The Google free version of that is Google Slides. So if you take this file and open it with Google Slides, you'll also get the slideshow. So if I just double click on it, it'll open it up. And then it'll open up the same slideshow we were just looking at, but on my computer instead. And I was doing it on the tablet because then I have the stylus so that I can draw, but here's the slideshow that we were just looking at. So this way you can look these up. Obviously, sometimes we don't get through the entire slideshow. So this is a great way for you to go and see the slides we didn't get to when we were in a Zoom session, when we don't get to the end. Today, we happen to get to the end, but you can also just pull this back up that way.
Appreciate it. Thank you so much.
Okay. So let's see if we take a look at a homework. Let's see if this puts us in a position. So let's say you're like, all right, we talked about 2.1. So I'm going to go here to 2.1. So I'll maybe go to assignments and practice problems for 2.1. And I'm just going to go maybe to problem number 10. Do we think our discussion would allow us to begin to think about this stuff? All right, so this is problem number 10 from the practice problem set on 2.1. Suppose ABC is a right triangle, so they're showing it here, with sides of length little a, little b, and little c, so they're showing those there. And right angle at C, so they're showing a box here to show us the angle C is a right angle. Find the unknown side length using the Pythagorean theorem, and so they told us 2 of the sides. Then we're also supposed to find the values of the 6 trigonometric functions. All right, so my writing will be much worse on this using my mouse, but I'm going to give it a try anyway. So we know C is 10, and I know B is 3. So the side I don't know is A. So I know A squared plus B squared equals C squared. So A squared plus B squared, B is 3, so B squared is 9, equals C squared. C is 10, so 10 squared is 100. Yo, that's terrible. So what does that mean? A is the square root of 100 minus 9, which is 91. So A is equal to the square root of 91. Okay, so now the unknown side length A is, so I want to put that in there. So I click in the box and I'd say, give me a square root of 91. So then it says, what is sine of B? So if I go over to B, and by SOHCAHTOA, sine is opposite over hypotenuse. Opposite to the B side is of B angle is little side B, which is 3. Hypotenuse is 10. So sine of B is 3 over 10. And then we would just continue that way. Questions about that at all? All right, so hopefully that puts you in a position where you at least could consider doing these practice problems. Now, keep in mind, let's say that you are trying these out, but you're getting confused. You could say, well, give me some more help here. What are my help options? Show me an example. Let's view an example. And then it'll bring up a problem just like this, where they just change the numbers a little bit, and you can just click through and they'll show you how to do the problem. So I'm just pointing this out in case you hadn't noticed how good this is to help you when you're practicing, that you can often see completely how to do a problem in case you get lost or confused along the way. Well, what did you mean by that? What did you want me to do? Well, you can get help here and they'll show you and they'll walk you through it. And sometimes there's different versions of this. View an example is usually the one that students like the best, unless there's maybe a video option, which might show up here, but view an example is the most common good one. All right, and we are about out of time.